about a carry skip adder. So what you mean by carry skip adder is, so when I pass any carry, let's say the carry in between input is equal to Cin is equal to 1. So in this diagram, so when I pass this, what we are trying to do is we are propagating it with 3 consecutive chain values. You can see the pass 1, pass 2, pass 3. So we are propagating these 3 values, and after that what we are trying to do is, so we are skipping the chain. So we are skipping the chain. You can see here we are skipping the chain. So means what? The carry has been propagated. The carry has been propagated for the first consecutive 3 passes, and after that it has been shift, or it has been, the pass has been stopped over here. And after that what we have done is, so we will be considering the next carry propagation by considering how many cell delays. So you can see here 1 2 3 4 5 6 7 delays. So means what? After 7 delays, so we are considering the one more carry which has been generated. Okay, so therefore what I can say that the additional time, the total addition time which is taken in order to do the addition of these bits, what we call it as, so it will be depends upon the longest change what we have passed. So in the longest change what we have passed is, you can see here 7 bits longest change what we have given a delay. So the first one we have given a 3 pass, for the next one we have given a 7 pass, and again for the next one we have given a 4 pass. So means what? The propagation delay or the time taken to do the addition, it mainly depends upon what is the longest pass you have given for the adder. In the case of carry skip adder will be taken care. So if I consider that, so the total time it has taken in order to do the addition can be represented as T is nothing but 7T plus K dash, we can write 7K plus K dash we can write. Okay, the total time taken by a carry skip adder in order to do the addition, we can represent it as 7K plus K dash. So what do you mean by K? So K is nothing but a cell delay. So each cell, if you want to do the addition, it will take certain amount of time. So that time we call it as a cell delay. The next one is K dash. So what do you mean by K dash? K dash is a time needed to complete the 11th bit sum by using carry in to the 11th bit. K dash, why? Because we are considering the first is 4 and the 7, next one is 7. So 4 plus 7. So 11 bit addition we are considering. So therefore this K dash is nothing but it is a time needed to compute the 11th bit addition. We need to note it down. So therefore the total time taken for the adder will be represented as T is equal to 7K plus K dash. So this is how we are going to make use of in a carry skip adder structure. So for that they have given you one simple carry skip adder. So it is nothing but a 24-bit adder they have given you. So for this 24-bit adder, what they have done is they have given a blocks. They have created a blocks of 6 bits each. They have created a blocks of 6 bits each. So you can see the first one will be 6 bits, the second will be 6 bits, and the third one will be 6 bits, and the fourth one will be 6 bits. Okay, so means what? The 24-bit it has been divided into 4 blocks, and each block is having a 6 bit of data values. So with the use of this carry skip adder, we can able to increase the propagation, we can able to decrease the propagation delay in the case of adder addition. And here also we will be using 2 important functions, that is nothing but the exclusive OR operations we will be using, and also the multiplication of the input sequences we will be using. So with the use of those 2, we can able to create, or we can able to generate a general skip adders. So this is one of the example what it has been given for in your syllabus. So how you can design by using a mux, that is nothing but a 24-bit adder. Okay, so this is one of the simple example. Okay, so now we will go for the next thing is, so how we can able to estimate the propagation delay which will be taken care in the case of carry skip adder we will be checking. Okay, so in order to compute the propagation delay which has been involved in this carry skip adder. So first what we need to consider is, so how many adder cell we have considered for the study, we need to consider it. So for the study, what we have considered is, we have considered as carry skip adder with consisting of n blocks of p adder. So whatever the step for the study, or in order to understand the propagation delay which has been incurred by this carry skip adder, if we want to calculate means, so we need to consider what is the adder we have considered. So how many block of adder we have considered, and in each block how many adder cells are there, we need to consider it. So we have considering for our study, that is nothing but, so whatever the adder we have considered, so it is represented with capital N, so which is nothing but it contains m block of each of p adder cells it contains. So therefore the number of cells, the total number of cells whatever we are considering for the scenarios, so it will be having n is equal to m into p. Okay, so this is what we will be having a general equation. So the next one is, so now what we need to do is, we need to calculate the time needed for the propagation of the carry signal through all the p adder cells. So because we have a p adder cells in each block, right? So we need to calculate the time needed by an each adder cell, which is consisting of 3 p adder cells, we need to calculate it. So therefore we can write it as T is equal to K1 into P. So what do you mean by K1? K1 is nothing but the time required for each adder to do the computation of the addition of the 2 bits. So that is nothing but your K1, and P is nothing but, so how many adder cells you have in each block. So that will be consisting. Okay, so the next one. So this K1 into P, what it is? It is a time needed to propagate the carry signal for the one particular block. So in the previous diagram what we have shown is, so we have shown 24-bit adder we have seen. So in the 24-bit adder, so the first block it is having 6 bits, the second block it is having 6 bits. So here we are talking about T is nothing but it is a propagation delay which has been exerted by the first 6 bit of adder. So that is nothing but K1 into P we have done. The next thing, so the next thing like this, how many blocks we have? So we have a totally p blocks of some of p m blocks of p adder cells we have. So for each block, so we will be having some propagation delay, so that we will be representing in terms of K2. So K2 is nothing but it is a skip what we have considered, that is a carry skip what we have considered from one block to another block. So that will be represented in terms of K2. So therefore the time needed for the carry skip through m adder blocks, so the total adder blocks if I consider means, so the time needed to skip the carry we will be representing by equation, that is P dash is nothing but K2 into L. Okay, so now, so what I can do is, so if I want to calculate what is the worst scenario, means what is the maximum propagation delay I can expect in this carry skip adder. So if I do the calculation means, so what you'll be getting is, your T is nothing but 2 into P minus 1 into K1 plus M minus 2 into K2 you will be getting. So M minus 2 into K2 will be getting, sorry here the K2 is missing, M minus 2 into K2 you will be getting. So this we call it as the worst case propagation delay which has been generated, or which is possible to generate in the case of carry skip adder. So we can able to expect, so this is the maximum propagation delay what you can expect from this carry skip adder. Okay, so and now what we trying to do is, we want to see what is the minimum propagation delay. So if I want to see the minimum propagation delay, what I am going to do is, I am going to substitute, that is P is nothing but n by m, because we know that m is nothing but n into p, right? So therefore what we can write it is, so P is nothing but n divided by m. If we do that, so I'll be getting how many number of adders for each cells I will be considering. So if I substitute that, so you'll be getting the minimum time required in order to get the maximum output, or in order to get the final output from this carry skip adder will be represented, that is m is nothing but square root of, m is nothing but it is a square root of 2nk1 divided by k2. Either I can write like this also, or whatever is there in this, that is also correct. So here what they have written is, so 2nk1 divided by k2 to the power of 1 by 2 they have written. Okay, so this is very important equations. So sometimes they may ask you in some of the competitive exams, and in most of the gate examinations they have asked you this question. So now you can see it. So this is the scenario where you are going to get a worst case carry propagation in the carry skip adder. So means what? The carry, if it is generated in the first block only, so that is wherever you are giving the Cn input. So if the carry is propagated in this first block only, then it has to propagate for the next block, and then it has to propagate this next block, and this has to propagate in the next block. So means what? This block has to wait for the carry to be generated by the first block, and this set has to wait for the carry generated by this block, and this block it has to wait the carry generated by this block. So this is a how we do the optimization in the case of carry skip adder. Okay. Okay. So this is how we can implement in the case of CMOS technology. So this is the circuit diagram what we will be using for the carry propagation in the. So the last one, what we call it as a carry look ahead adder, CLA, carry look ahead adder. So why we go for this carry look ahead adder is, so in order to improve the ability of adder to predict the next stage of the carry generation. So in order to improve the ability of the adder to improve the next stage of the carry generation, so we will be going for this carry look ahead adder. So this carry look ahead, generally it will be used frequently when you compare to the carry skip adder and the general adder what we have considered. Okay, so with the use of this carry skip adder, so we can increase the performance of the adder. So in order to increase the performance of the adder, so we are going for this carry look ahead adder. And you can see here the given expression, what is that? Ci is nothing but g1 plus gi minus 2 into pi minus 1 plus gi minus 3 into pi minus 2 into pi minus 1, like that, so on it will be going. So means what? That is the expression for the carry for the nth bit. That is the expression for the nth bit. So in order to understand what exactly it is doing, so we are considering a 4-bit carry look ahead. We have given it over here. Okay, so the first 4-bit, right? So therefore what you have, you can see here, you have a S0, you have a S1, you have a S2, and you have a S3. Okay, so you can see here the first S0, what is this? P0 into G0. What do you mean by P0? P0 is nothing but it is a exclusive operation of your input terminal, that is A and B. Exclusive operation of your input terminal A and B, that is nothing but A XOR with your B. A XOR with your B. Okay, so this we call it as a propagation function. So what do you mean by G0? G0 is nothing but a ANDing operation. So what is this? It is nothing but A into B. A into B. Okay, so this is the sum expression and this is the carry expression. Okay, so now how I can generate the second generation, means the second carry, how I can generate, that is how I can generate the first second carry C1. How I can generate? So I can generate by using this manner. So how I can generate? So if you consider a full adder, so the first we call it as a half adder. So if I consider a full adder means, so I can generate the carry in this manner. So how I can generate is, so that is nothing but your C1 is nothing but your G0 plus into P0 into C0, your P0 into C0, your P0 into C0. So what is this G0? G0 is nothing but your A into B, your A into B. What is this P0? P0 is nothing but your A XOR with B, A XOR with B into C0, A XOR with B into C0. Okay, so therefore you can see here I have represented into P0 and this I have represented into G0. Similarly, if I want to go for the third bit addition of the carry, so how I can generate? It is nothing but second bit addition of the carry. If I want to go, how I can generate? G1 plus P1 into G0. So for this, I need to multiply with the P1 I want to multiply. So what you'll be getting? So P1 into G0 plus P1 into P0 into C0 you'll be getting. So similarly for the third bit carry, how I can generate? G2 plus, so for this I need to multiply G2 plus P2 into C2. What is P2? P2 is, what is C2? With this one. So therefore P2 into G1 plus P2 P1 G0 plus P2 P1 P0 C0 will be getting. So similarly for the last carry, so what will be here? It is G3 plus P3 into G3 C3. So what is P3? P3 is this. What is C3? C3 is nothing but this. So I need to multiply over here. So if I multiply this, so therefore you'll be getting this values. So now what you can see, so by looking at these generator polynomial, that is the generator polynomial and the propagation polynomial, so we can create some more expressions, or we can create some more expression. So what is that some more expression is? That is nothing but your P3, P2, P1, P0, C0 is the right. So how I can write? I can represent with some other notation, that is nothing but I can represent it in terms of pi. Similarly, your G3 plus P3 plus G2 plus P3 into P2 into G1 plus P3 into P2 into P3, the remaining thing. So the remaining thought, whatever is the right. So this I can represent it one more variable, that we call it as a lambda, that we call it as a lambda. So therefore, I can write the carry which has been generated in the fourth bit, that is nothing but your C3. What I can write is your pi plus will be your lambda you will be getting. So pi plus your, sorry, this is the gamma what I will be calling. Okay, so this is the fourth bit carry what you will be adding. So for that, so this is the diagram what we will be using. Okay, so you can see this is how we can create a logic sum, and a carry how we can create. Okay, so I think if you are seeing, or if you remember in the logic means in the digital circuit lab also, I think you have implemented this carry look ahead adder with the use of this XOR gate. So if I am correct. Okay, so means this carry lookup header, it is also called as a ripple adder. Ripple adder also it is called as, why? Because the carry of the previous one, it has been propagating and we are trying to estimating that carry in advance. So therefore it is also called as a ripple adder.